Hello and welcome to this podcast for Electropages. I'm your host, Robin Mitchell. Today we have a fantastic guest, as we've had many times in the past. We all love him, we all know him. It's Travis from Omnetics. So without further ado, please introduce yourself to the audience, what you do, who you are, and what you like to do in your spare time.
Righty. Travis Neumann. I'm actually the special projects manager here at Omnetics, and really what that comes down to is a lot of support for sales, engineering, manufacturing for new products. And I've been here for 8 years at this point, a little over actually. And let's see, the spare time question is interesting because that can vary by the day. So it could be CAD. I've got 3D printers at home. I actually have a 5-axis CNC in my garage, or it might be house projects. It could be anything. So kind of a wide range of things going on at home. Just depends on the...
And so basically, just like the many engineers that we've had on this show, you also don't understand what it is to have proper free time where you're not working.
A fair statement, because it can very much be I'm in charge of my time, or potentially the wife might have some ideas for me as well, and that's okay.
And so you're constantly torn between things you want to do, but are still work related, and then someone else coming in, taking over your time, making you do things you don't want to do. And then the concept of free time where you're not actually working, as I don't understand, we basically just spend all our time stressed out all the time doing some kind of engineering project or work for someone else.
Yeah, exactly.
Basically.
It could be, it's kind of interesting because it could be, it's just sticking on the home theme for a minute, right? It could be something crazy like doing some CAD and making a really fancy soap holder, if you will, or doing because I use Fusion at home. I have SolidWorks as well here and at home, or it could be we could be making some. I did a horizontal railing in SolidWorks as well. But anyway, Anyway.
Oh, nice.
Just like the look, but.
Personally, I'm more of a free CAD user.
Fair enough. I've never used it.
But, if SolidWorks floats your boat, that's absolutely fine. I totally get it. I'm more of a free software, open source kind of guy, but I get it.
I actually cut my teeth many years ago. I started at a position as manufacturing engineer and never used SolidWorks in college. This was back in the day when they actually had CDs, so date myself there.
You get the serial number as well.
And they gave me a version of SolidWorks to take home and just figure it out. And I used that to make some molded parts so we could transition from machine parts. We were spending like $60,000 a month on these machine parts that were consumable. And then switched it over to molded, and we're getting them molded locally for 75 cents a piece. So the spend went from... it was over 90% reduction. It was nuts. So.
Well, I hope you got your value out of it. The amount of money you're saving the company.
It was more about, and it was really just supporting manufacturing again. And that's been my career, 25 plus years at this point, is really been just centered on manufacturing.
And I'm guessing as well that this was during the time when software was a buy once and then you had it for life instead of some subscription service where you're paying $100 a month just to have the privilege to use it.
There. Buy and use versus the service business, right? So.
But this is a really interesting conversation because this actually brings us to the thing that we want to talk about today, which is the 3D printing. Because as you said, the cost reduction from going from machining to molding was an absolutely massive step. But tell us a little bit about this 3D printing situation going on.
I'll just, in terms of what we do at Omnetics, I'll talk about it like that. We've moved into 3D printing some number of years ago. Before I ever started, they had a FDM printer that they were kind of, I'll say it, playing around with. And then I had moved in here from another company. We're basically doing like consulting type engineering. And then we've had quite a number of parts since then, just because of some of the background that we've been doing 3D printing. I had thinking I had some show and tell sitting on my desk. I don't, and I haven't sent it, any pictures to you guys for this, but we've done some things like, let's say we need a rubber component, okay? And this is just the idea of 3D printing. So let's say we need a really soft rubber component. One of the things that we've done in the past is we will print what I'll call like an eggshell type of a mold, right? So you've got your part in CAD, and then you can make a surface around this part, and then you put somewhere to inject, somewhere for a vent. You inject your silicone or whatever material you need to use, and there's some really great ones. The name escapes me right now, but there's some that you can use for like customized hearing aids, so they fit your ear canal, so it's great for flowability, that sort of thing, and it cures in like 15 minutes. And you shoot that stuff into this 3D printed mold, you let it set up, and then when you're done, crack it like an egg. You can get rid of all of the molded parts, and then you're left with just your rubber component. So, which is a neat idea if a person wants to make like a face seal between the two connector surfaces. Maybe you've got, pins and sockets, and you want something, some kind of interfacial in there. Or we've even done that with something with a more kind of elaborate cavity, where it might have like a little hourglass shape or something of that nature. So that way when you're pushing a wire through it, that narrowed down silicone portion can seal off on that wire, right? And it's really just the idea of getting prototypes. So bigger stuff generally, but we've got a few printers that we use here today in Omnetics. Formlabs is very popular. We've got 3 different Formlabs machines here. We use those in manufacturing. Generally, we'll use them to print. Oh, my picture's going out of focus a little bit. But generally, we'll use them to print like big fixtures. We can do that sort of thing. Something we'd put into like maybe an oven or that. And then more recently, we had a 3D Systems printer in here, ProJet 2500. Great machine. So if somebody wanted a custom housing, or maybe they wanted a different configuration of the pins and sockets, what we could do is we could go and we could 3D print some of these parts. I mean, you can't even see this on the camera. Some of these pictures I sent. This is a bigger one for us. You can go and 3D print some of these guys, right? It's stupid tiny. And then that way you can get a rapid prototype made and sent off to a customer. And a lot of times, they're not going to do like you're not shock and vibing this guy like you're simulating it being launched into space or on some ground vehicle or whatever. You're not doing that. But what it'll allow you to do is it'll allow the engineers to have hardware to prove out their system sooner rather than later. Right? Because I can make some little housing in a day, versus if I'm going to go and machine something, it's going to take, there's machining, there's plating, there's all sorts of other steps involved with getting a prototype sent to the customer.
Now, one thing I want to quickly ask you is, because from my experience of 3D printing, and anybody who's used not commercial, but sort of like the maker end 3D printers, the small desktop printers, we all know that the resolution and the accuracy they provide it's not great, compared to something like a machined part using a CNC. But if I understand correctly, you guys have done something about that, haven't you, with your 3D printers?
Well, so interestingly enough, we just moved in. The 3D Systems machine, that one's had some issues. We ran the wheels off of that guy. Great machine. And we recently picked up BMF 1025. It's Boston Microfab. And the big thing about that is the 1025 is all about the resolution. Okay? 10 micron, 25 micron. We've been working on doing just like you would any kind of, call it off-the-shelf resin printer. And interestingly enough, you can use the same type of like calibration parts, where it has like an infinity symbol, and you're looking to see if the edges are blended together, or if it's, if it's broke apart, whatever, to figure out the exposure. It's the exact same ideas. So we've spent a fair amount of time with this machine. We've had it 2 months maybe now at this point. We spent a fair amount of time with this machine, really getting settings dialed in, specifically so far around the 20 micron and 40 micron on one specific material. And like any material you'd buy for a resin printer, any printer really, you got to come up with a.
So when you say 20 microns, are you talking about dimensional accuracy?
Correct. Yeah, the 3D Systems printer, and I'm going to flip flop now between metric and imperial, but that's what it is. Yeah, you'll forgive me
God.
later. So,
here we go. Go on.
The 3D Systems printer that we had was the ProJet. We would regularly print parts, and if anybody asked what we could do for like a tolerance on some feature, I'd just say it's plus or minus 2 thou, 50 microns, whatever. So, yep. So I'm like, that's about what we're gonna get. A lot of times we could do better than that, but just safe to say that's what it is. This particular machine we've got here is very much what it is. So if I'm saying 20 microns, yeah, we can get that. And we've done a bunch of.
That's absurd. But that's absurd for a 3D printer. 20 microns, because you have to consider that the extrusion will have a degree of expansion and the layers adding together, and with all of that considered, you're still getting 20 micron resolution.
Yeah, and the crazy thing about this particular machine is, well, here, like if I have this part, let's say, right, and I can't show this necessarily without putting up CAD or whatever, but. There's a larger clearance bore in there, and then the bore gets smaller for the remaining portion of that the contact's going to get loaded in there. So, like on that guy, what we end up doing is we can do like time and intensity and all of that by layer if need be. So just like it again, this is the same idea. So if you've used a whatever, Elegoo printer or Formlabs or whatever, and you know how to, you're familiar with how to calibrate or whatever, same idea applies here. It's just the software is a little bit different. And interestingly enough, slicing software for that isn't proprietary for this particular machine. But anyway, so you can change the settings by layer to be able to make sure that you're hitting the precision or the accuracy that you need to be able to get these parts done. And that's the big thing, and that's why we've spent a lot of time and energy really just coming up with what do those parameters need to be for the intensity and the time by layer to make sure that we're within tolerance. And the reality is you could do that. As long as it's within print, rock and roll, we're good to go.
And you also seem to mention 10 micron as being possible as well.
We have not tested that yet, and there's some other things that we've found out. We were actually the first one of these machines in the wild. Okay, so there's some other things that we've been learning about the machine, and we've actually CAD'd up and remachined a few parts that are used in the machine specifically. So here, okay. Yeah. All right, full disclosure.
That's insane.
So you have a membrane, right? You have a membrane, and the membrane is the way this printer works is the membrane sets the membrane in the platform. The platform starts here and it moves down into the fluid. So the membrane sets your height. Well, we found that there was a little bit, and I mean the tiny little bit of twist on that frame that held the membrane. So when we had test parts we put down at different intervals on the plate, and then measured them, and then eventually we're like, this doesn't make sense. So then we checked the membrane, and it's like, oh yeah, or the membrane frame, and you can see, oh, there's a little twist in it. So CAD'd some stuff up. We made our own membrane frames, that sort of thing. So all of that stuff, when you get into that level of precision with any of these things, I mean, again, this thing's got 30 some holes in it that you can't see.
I'll be honest, all the camera
Yeah.
shows is just like a solid block
Yeah.
of color of about the size of a fingernail.
Yeah,
It doesn't
that
really show
whole
anything
part
else.
is about 7 millimeters on my little ruler here. Yeah. So.
Oh, that's ridiculous. And but to think that why does it not surprise me that Omnetics is the kind of company that gets a 3D printer, the first one in the world, and the first thing it does is goes, nah, not good enough. Let's go in there, take it all apart, rebuild some parts, remachine it, and get it back together.
Oh, you gotta figure it out somehow. And that's really what this area is about, right? So back to like, if a customer has some concept they want to try, great, let's give it a try. That's what this area is about. It's like, okay, we don't have, a lot of times you come with something and you want to make some interesting thing. We don't have a work instruction. It hasn't necessarily been done before. So it's like, this is very much figured out.
And that's what makes the special projects division so unique, in the sense that if a customer has a particularly weird problem or needs some particular machining or something that they can't get in the wild, it's a case of you guys are just sort of like, well, let's just try and see what we can do, which is honestly not something you can get from most companies, because most companies would essentially turn you down and say, look, we're not interested in doing something that deviates out of our standard procedure.
Yeah, I mean, now granted, like, we'll do prototypes and whatnot, and at some point there might be an ask for, it depends on what it is, right? There might be an ask of, hey, you know, we need this is some crazy material because maybe you want to do molybdenum for space shielding or whatever. You're going to have to, there's a little bit of money involved in it, but again, we're not necessarily going to turn it down just because of that. We don't do, one of the things is like, we don't have minimums. You can order one of whatever. The reality is it's costed accordingly or priced accordingly. So, up to you.
And so when it comes to the use of 3D printers, I suppose one technical question I've got is, do you take advantage of sort of like orienting parts in certain directions to make sure that you get the best print out? Because, you know, because the X, Y, and the Zs will always give you different sort of tolerances, different behavior as you print the structure. So do you find yourself often printing things at 45 degrees or something like that to try and get the best of different axes?
Interesting question, actually. A lot of
Can't answer it. It's trade secret.
I'm not worried about that. I'm going to say that's a path for you to figure out. But a lot of these type of parts will just go direct on the bed. There's no 45. There's no nothing. And that has a lot to do with what this printer's about too. I'll tell you that. So most of the time, if we're going to go after something, because like this machine is so does such a good job, we might even take a part like this and orient it in a thinner direction just because of time. That might be all I care about. It's like, well, okay, it's whatever. Today I want to get them. I want to get a shot at this today. Let's just flip it 90 degrees and lay it flat. And then worst case, we might have to have some support in there that we sand or clean up, just like any other machine. But I can tell you already, I know the holes and stuff are going to be on the point, so I'm not worried about that. So it might be just time. And most of what we're doing is right on the bed. Right on the bed.
And I think that's a really good testament to how much 3D printing technology has changed in the past sort of maybe 5 years. You know, go back 5 years ago, you'd probably have all kinds of problems that you've got to try and figure out, printing different orientations, as you said, different rotations. Now they've become so good, you just go, well, I want it a bit faster, turn it this way. But besides that, in terms of the quality and the structure and the precision, it doesn't really matter. Which kind of brings me to another point, which is that, as you said before, the transition from machining to molding gave you like a 90% cost saving in producing parts. What kind of cost saving do you sort of see when you use 3D printing technologies when prototyping new connectors and moldings?
If we just need a few, and when I say a few, in my world, that's like 10 or less, okay?
Yeah.
I can go and take the CAD. We're not doing it. I'm going to just start with this because I know this happens a lot to engineers, okay? We don't change the CAD. We don't even mess with it. We don't make CAD for 3D printing, none of that. So we'll take whatever CAD you have. If it's machine CAD, fine. If it's CAD for a molded part, fine. Doesn't matter. So we don't change the CAD. And I need 10 of these. I can have these tomorrow. and I'm saying, because just how we do it, we generally start the machine at the end of the day. That way, if anybody, special projects is a different than engineering. If engineering needs something, if manufacturing needs something, we can put all of that onto the build plate. We hit go, and then we aim a lot of times to have it finished by the time we come in the morning. So I can have this part by morning. Now, if I need to have that machined, it's a whole other animal. So we have material at our machine shop. Generally, this part would be made out of PEEK because you're not doing LCP or PPS. You're just not doing it. That's what you normally mold it out of. But then I've got to go and if let's say I don't have a program, I need to program it. You could burn a day on something like this, and then load up the machine, do the setup. Generally, we'd budget like 4 hours for that. Generally, if it's some new thing, if you're doing some one-off new thing, maybe got to mill some vice jaws, blah blah blah, and then it's still going to go through. Maybe not. It'll go through inspection if it's just for some kind of prototype thing. So if I was getting a favor, I'd say it's probably a week, right? And that's if we got machine time and everything.
And then when you consider the fact that with a 3D printer, you could get 5 of those all printed at the same time in the same machining cycle. Whereas if you're going to machine them, it's machine them one at a time. But there's another thing you said I thought that was really interesting, where you said, well, we print at the end of the day because we wait for maybe engineering department to come in, which then goes to show that single 3D printer is then doing jobs from multiple departments at the same time.
Yeah, 100%. I mean, I'll say this too. The fluid is relatively expensive for this, but now going back to the cost portion of it. So, I mean, there's not a lot of material in here. This isn't going to be, let's just say, for the sake of discussion, this is a $5 part. Let's just say it is. Now I'll go back to the machining thing. Let's say I burned a day doing programming and setup, and I'm making soft jaws, and I'm making 10 of them. It's like, I can't buy soft jaws from, pick a website. I'm going to have more into just the soft jaws for 10 parts than I am anything else. So, and then there's machine time and everything else depending on what your shop rate is, blah, blah, blah. So then if I machine 10 of these might be $200 each. I don't know. I'm just making up a number at this point versus, let's call it 5. So
And then to add on to it, if you wake up in the morning, you get to work, those parts aren't quite what you wanted. That's all right. Make a slight change in the CAD, put it back in, and then wait for the next day. And then that's the next iteration of that prototype. But if you machine them and then they're wrong, that's a week gone and the $200 per part, depending on the price it would be. But like you say, I mean, I can personally imagine it probably costing more if you consider the amount of time that an employee's got to set it up, get the right material, feed it in, make sure it's going to work, program it. Whereas with a 3D printer, it really is a case of just print, walk away, come back.
Here's the other one. Like, we might have, let's say we're making a board mount connector and somebody wants us, this hasn't happened, but I'm making this example up. If somebody wants to make, they're doing a board mount and they want to do like a special through hole or something of that nature, what we would generally do there, because we have some connectors where there's many kind of layers of leads bent down for horizontal mounting. And what we would generally do there is we would 3D print the tool. And it's to your point, because I can 3D print that. I can try something tomorrow, let's say, and let's say it fails. We're okay with failure. It fails. Then we can iterate it. Maybe we got to change some dimensions, this, that, or the other. The bend angle's not quite right, whatever. We can run another one. And then once we get that process fleshed out, and maybe we got a half dozen 3D printed tools we've just thrown away. Maybe we do. Once we get that process fleshed out, then we say, oh, here's what I need, and then we'll go and have it made like in hardened tool steel, right? So then everything's EDM'd, it's surface ground, it's the whole 9 yards. And you know that you're not having to iterate on some hard tool because you've already done it all over here, quick and dirty, if you will, on the 3D printing.
And I think as well that even the best engineers, and I've seen it countless times, where they design incredible stuff and they are very good at their job, but it is true that sometimes you can have something completely obvious but not obvious at the time. So let's say, for example, you take that connector and they go, oh crap, I forgot, it's got 3 holes, this one, not 2, and so it won't fit on the board now. And so it's a case of, oh, well, okay, I can put, it's happened to me, it happens to everybody, you know, you're working on design and there's just something you miss or forget, and it's completely obvious, but you don't realize until you've got a physical part in front of you and you go, that's not going to fit.
Prime example is, I can't show it, but let's say there's one in the lab right now. It's actually a harness, okay? And it's using, there's Omnetics connectors on there, there's Neumann connectors on there, there's some D-sub, I don't know who those are from, doesn't matter. And interestingly enough, this is to the does it fit type of thing. So one of the D-subs has a back shell on it, okay? And it's a fairly big D-sub. I think it might be a 100 position or something like that. Well, you've got a lot of wires running into this, and many of them are shielded, twisted pair cables. So now, instead of it just being, let's say, 100 wires, now I have 50 of these cables that I'm bringing up to this guy. Okay. Well, twisting and shielding basically expands like the cross section of this guy. So now we're looking at this and it's like, well, that's interesting. We need to figure out how we're going to make this happen. So
it sounds like the Jaws phrase might be quite applicable here. We need a bigger boat, or in your case, a bigger cable.
It is. It's like, well, you know, the customer had this design they come with, and it's like, okay, yep, we'll give this a try. And now we're looking at it, and it's like, it could very well be time to make some recommendations on, hey, we can use a back shell, but we need something with a oval-shaped entry or something of that nature.
Of course.
That way we can take all of these, there's not really 50, but all these cables, and we can get the shields terminated around the band clamp, and then still have enough room for all the wiring to get through. So, yeah, very much so. And we've 3D printed the back shells just because, again, it's a fit, form, function type thing, and
it's quick, gets straight to the point. You know if it's going to work, and then once you're sure it's going to work, you can invest in the money in building a proper one.
The back shells are like 26 weeks lead time, so.
Oh right, okay. Well, I think they want them now.
This will give them an idea of what's going to work, what's not going to work. Now, rather than wait 26 weeks, find out that this is going to be an issue. Yeah. And then it's like, well, crap. Now we got to order something else and wait another 6 weeks.
Well, that's actually a really interesting. That's actually a really interesting example because, like, imagine if we didn't have the 3D printing solution, we had to wait 26 weeks. Imagine waiting 26 weeks. Your back shell arrives, and you go, that won't work. But if we use this other one, which was available 26 weeks ago, it would have worked fine. Now with the 3D printer, we can go, oh yeah, we can go for that back shell. It will be available tomorrow, and we don't have to wait for the one that's not going to work in 26 weeks' time.
And then the other thing is, too, is depending on what it is. So those are D-subs. They're pretty big. They're big guys. So a lot of that stuff, we might not print it on this printer because we don't need the precision, and we'll print it on the Formlabs. There's a ton of it because of we've got a lot of materials available and that sort of thing too. So we mix and match depending on what solution we need. Yeah, and it's all about saving time.
So a few minutes ago, you sort of mentioned about how like a lot of these prototypes are prototypes. You use them as a way to make sure that the design is going to work before you commit to something more expensive. But considering how far 3D printing technology has gone, we're seeing some, far better resolutions and precisions and accuracies. Do you not think that maybe another 5 to 10 years, these 3D printed parts could actually be usable in a lot of these applications as a first trial run part? So, if you're only making maybe 100 to 1,000, it's just easier to 3D print them and then use them in those applications.
And I'll say, I don't think you have to wait, right? I don't. So I've just been talking about plastic printing. That's what we have here. We've actually had shells. I'll call them shells. We've had shells made from 3D microprint in Germany, which is it's a cool website to look at. Just go to their landing page and you can see some of the things that they printed, and they're crazy small. And we've done some stuff here in the States with Trio Labs, because they're like super fine resolution 3D printing as well. So Some of that stuff you could even if let's say you wanted to have some fastener get in there, you might have to do a little CAD work. I don't know, but you could get them to even 3D print like threads in metal,
Oh,
and then
blimey.
couple that with some other thing like you could print the plastic part. You'd be down to someone putting the Legos together effectively. So,
Oh, actually, that's a
yeah.
good. Actually, that reminds me of something. So you guys right now are working with the plastic and the liquid printers. I'm guessing it's something like an SLA or is it a
Yeah, go with
DLP? Is
that.
it? What type is this? Is
All
it
of that stuff is
yeah,
like
DLP?
there's
Yeah,
so many acronyms and stuff. I don't pay attention to that. It's a resin
yeah.
print,
It prints.
right?
It prints plastic. That's all you care about. So with that topic of printing plastic, do you think Omnetics is going to be getting themselves a metal printer at some point?
Great question, and I I think for where so if Omnetics is gonna get it, I'm gonna be the guy that's picking it up. I'm sure of that. Um, when I think about that, we would have it really comes down to the business case in my mind. If we had a ton of applications where our spend was high enough that I could justify it, I'd say yeah. But then at the same time, I think about, well, now I got people wearing all this respirator equipment. Do I need another special room? Da da da. Maybe, maybe not. If it changed kind of from what it is now, possibly. Possibly.
Because what it sounds like to me is that when you talked about like back shells and machining metal parts, for example, if 3D printing a metal part could be just
yeah.
as good as that machined part, it would sound like it might be an easier option for Omnetics. But having said that, I'm now also thinking of another possible opportunity that could happen maybe 10, 20 years down the road. Do you ever see 3D printers being able to print the entire connector, both plastic and metal, in a single pass print where you get all the connections, the electrical connections and mechanical connections in one go?
I think, again, this is all we're just kind of thinking about ideas here. In my mind, the biggest hurdle a person would have to overcome is, no.
Metal,
Honestly,
I imagine curing
do
the
I think
metal,
there's
I
a
would
way?
imagine.
Yes. It would have to be right now. It would have to be some dual head thing. This is just me thinking about this. And
Yeah.
because then you could laser like powder. It might not be at the exact same time. It might not be simultaneous because of what it is. It might be some idea similar to like insert molding or that sort of thing. Maybe.
Oh
Maybe.
yeah, so you're printing the plastic part and then you insert
and
as
the
you're
only reason
printing.
I'm saying that is because my thinking is locked into how things are done today. Yeah, and because it'd be like if it's a powder bed thing, whatever, it'd have to be some dual head business. Yeah, there'd be some secondary processing, but do I think you could get there? Possible. Yeah. Otherwise, your other hurdle would be right now. A lot of that's sintered if you're not lasering it in, so there'd be a whole thermal thing. But I'll say this: we haven't ran it yet. We also have a ceramic loaded material. Okay, so in terms of the idea of something that would be able to handle like a wide range of temperatures, let's say for space would be one, or oil.
I was going to say volcanoes, but
so yeah, maybe we're doing sulfur monitoring, whatever. But we've got some ceramic material that you could potentially just print the whole thing as one monolithic piece, and then do your contact loading and that sort of thing. So in essence, you could print the whole thing today. Same idea as like an insert molded connector or that sort of thing. And there's people that do that now. So.
And have any of your customers moved to entirely 3D printed parts as a final part yet, or do you think there's still that kind of hesitation around 3D parts to be used in an end application?
Somebody has to break the ice. So a lot of what we do is based on history. Heritage is a common word that you'll hear like in space, right? That nobody wants to be the
you know, I hate to call people out, but it kind of reminds me of those first SpaceX rockets where they had all the touch screens inside and everyone's like, this is so modern. And I'm thinking, I'd rather be in a Russian Soyuz because at least I know it's not going to crash because it's still got all the buttons and the clickers as opposed to the touch screens, which you have no idea if that's going to survive orbit.
Yeah, and years back, I remember this engineer I was working with, he had made the statement, I'm never the guy that eats at the new restaurant, right? So the thing would be
Yeah.
is you would need a company or some sort of thing of that nature for them to have a program that they put the part into. It's done all of this qual testing, all of this business, so that way the next person in line comes up and they're like, okay, I can use what these individuals over here have, right? And they've been flying this thing or whatever for forever and a day. And that gives me a level of confidence that I can use it in my application. And like there's stories of 3D printed metal, 3D printed parts for aircraft and that sort of thing. So I would say it's a matter of time. It's a matter of
Well, I know there was that recent rocket launch that was entirely made. The engine itself was 3D printed parts. So with some luck, maybe they'll contact you and use one of your connectors as a 3D printed part.
That's fair. Whatever you need.
But in terms of 3D printed parts for yourself, what would you say has been the most exciting project you've worked on?
I think the things I find the most entertaining, let's say, okay, again, this is 3D printing for some custom solution, would be if we have to do like the eggshell molds and that sort of thing. Because it's so
Eggshell, yeah.
in an essence, it's like such a contradiction to what it is, right? I'm printing this to destroy it, literally to destroy it. So then you're playing this game of like, okay, back to what we chatted about earlier. Does it have to be oriented a certain way? Blah, blah. I can't, because maybe I can't have supports in this thing. I need the cavity to be, consistent and all of that. Some of that type of stuff is really interesting to me. A lot of times is, like I said, we'll 3D print things that you just can't get today, right? So I think that's probably it. And then just for me, the other one for me is, again, I can put this up to the camera, but you're not going to see anything, is just the sheer size of the features that we can get done now and the aspect ratios of the holes and that sort of thing through these parts. That to me is really cool. And the fact that I don't have to do a whole bunch of juggling of CAD or anybody else in the area needs to do a whole bunch of CAD changes and that sort of thing to really make it happen. I think that's fantastic.
And would it be right to say that Omnetics, because of the experience that you've got with the 3D printers and the fact that you've been able to make physical changes to the machine, you've done a lot of experimentation, that would make you one of the few in the industry, if not the only, who can print with those kind of resolutions and precisions for connector back shells and moldings and other parts for connectors.
Yeah, I think it just comes down to whether or not a company is willing to invest in the technology, right? So BMFs, obviously, we've done parts with those guys for quite some time. So, it was a matter of time before we stepped down into that range of size. And I can say, just from kind of going to trade shows and other things too, that there are other players in that space that are even smaller features. So believe it or not, and names, whatever, you'll have to do the Google search. But I know there's like an Israeli company that'll do single-digit micron features. It's crazy.
Oh. But I don't understand how that's ever. I mean, in what? How does a connector need such precision in the micron range? It makes no sense. What are you doing at that point?
Too, if you think about where things were years ago to where they are today with speeds, one of the big things with speeds is, with wiring and that sort of thing, is impedance, which has everything to do with spacing and that sort of thing. So as speeds increased, all of these sizes have really had to physically decrease. So if you want to keep picking up speed, obviously you're looking at finer and finer features, right? That's one of the things. Or your other option is parallel pathing and that sort of thing, but then you don't necessarily save the real estate. So you, you got to pick. Now, is there an endpoint? I don't know. Probably not, and that's okay too. But yeah, the actual stuff that they were doing on those, I want to say that was a medical application. So.
And so in that case, micron level connectors might be quite important if you're doing maybe something like neural bridges to individual neurons that you're trying to pick out of, or nerves out of someone's body, and you're trying to get wires from those to some tiny connector. So I can understand maybe in a medical application, but still, it's such an absurdly small
and I'll
size.
say this, in the last few months too, again, you're not really going to see this. I sent some pictures earlier, but we've also been working with, this is a tough C. There's actually,
that's absurd.
Believe it or not, there's actually 6 wires in here.
2?
Yes, sir.
6 wires?
Yeah,
I can see 2.
So we've been working in terms of reducing size as well, and rightfully so. It has everything to do with applications for space, right? Where aerospace, where weight and everything is at a premium. Medical as well. Right, surgery tools, that sort of thing. You don't want to make a hole bigger than you need to if you're doing surgery for somebody. So as the features have shifted down and everything else, we've even, like I said, we've even started working on shifting down our wire size. So yeah, this guy here there's actually 6 wires in this. I've got another one here this one's maybe easier to see because I have it wrapped up quite a bit. Yep, that one's twisted there, that sort of thing. So. All enamel coated, different laser technologies, all sorts of things to be able to strip that properly and whatnot.
Did you just say you need laser technologies to strip the wire?
There's a multitude of ways you can strip wires like this. The biggest thing for us, and this has everything to do with quality, is we'll use lasers to strip the wire. Reason being, it does not damage the actual conductor. Okay, so we can ablade the enamel, that sort of thing off there. But when you've got something this small, let's say if you're going to use a more traditional method of maybe just kind of like burnishing it off, or even
I was going to say using your teeth, but you know,
chemistry is another option. Well, then the other issue you've got is how do you control that position, right? And that's a big thing.
That's a really good point, because I'm sure any engineer worth their salt has stripped tons of wire, and one thing you always do notice that no matter how accurate you try to be, you'll often find you're trying to sort of like break it off at that point, but it'll end up being here or just before. And so, like you say, when you're talking about wires that are so small, you have to use a laser to just get that precision as to where that sheath is being removed.
Yeah, and that's the thing for a lot of our small contacts, that strip length will be 5 thousandths. The tolerance on the strip length might be 5 thousandths. Oh, and that's just, again, the stuff's small, so as it decreases in size, all your tolerances you have less range to work within as well. So yeah, it all scales.
And so with all of this said, sort of looking into the future, where do you see this technology going, and how do you see Omnetics sort of adapting to use these 3D printing technologies?
Well, we do have some things we've been working on. They're not out in the market, that use 3D printed shells, metal. And so we're kind of putting our toe in the water for that. I'll say it like that. The big thing is for customer use, end use type things. Again, if somebody wanted to and they're willing to do their testing, that sort of thing, great. We could do that 3D printing. Generally speaking, though, just dollars wise, if you have enough quantity, you're better off going with something that's molded. It's just what it is. So it's really tailored to whatever in my mind, it's going to be tailored to whatever the ask is from said customer. That's really it. it's
Yeah.
business case.
These technologies are just essentially allowing customers of Omnetics to rapidly prototype their designs a hell of a lot faster than you ever could at a much lower price, as we discussed, where if there's a back shell that you want to use and it takes 26 weeks to get there, you find out it's not going to work and you can find an alternative before you even have to wait for that one to arrive.
That's the big one. And I'll be real with you. I mean, we've done some crazy things that you're probably not supposed to do. We've used material that's good for 90C and we'll print and use it in the overmolding machine. So we're shooting 200C plastic into it. Again, if I only need it for 5 or 10 shots, what do I care? I'll just print more molds. Doesn't matter.
And that's the point. And the impression that I really get is that Omnetics is really pushing every barrier and boundary it can possibly find to figure out what it can do with the technology that exists and how it can improve it.
There's no rules here saying you can't. So I think it comes down to, at some level too, it's like, I think it comes down to, are you just willing to do it that way, or are you willing to give it a try? May not work, that's okay. Yeah. But the real thing is, if you learn something by doing that, I'd say it's still not a waste. It's not a waste. So
I really do feel like that Omnetics slogan really should be "Here be dragons."
It should be what?
It should be here be dragons. Have you ever heard that phrase? Here be dragons. So very quickly. In the past, when they used to sort of like do all the cartographies and the maps and stuff for like the 17, 16, 1500s, there'd be areas of the map where they didn't know what it was. So they put monsters down. So they say, here be dragons or here be monsters. So in the case of Omnetics, that slogan would imply that you guys are so at the forefront of testing technologies, no one even knows what's there. In terms of the precision, the quality, the capabilities, no one's actually done it yet. And so as the phrase goes, here be monsters or here be dragons. And so it's a case of like, no one really knows what's at this point.
Fair. That's fair. Yeah, again, and I think about it too as like, it's a lot to do. It's just mindset. If you're willing to take a shot at it or not, that's really it. So we are very much here to support, I said, we're very much here to support sales, engineering, and manufacturing. That's what it is. Yeah. So if somebody asks for help, that's what our job is.
Maybe a better slogan would be "Where no man's gone before." That might be more relevant for modern audiences.
That's right.
Fantastic. So just before we wrap up this podcast, I've got one more question for you. For the audience who are watching this video, if they want to get involved with Omnetics and the new solutions that you guys are providing, what would you recommend that they do?
There's a few different ways you could go after it. We have reps across the globe. So if there's something that you're not finding on, let's say, Omnetics.com, and again, that is a thimble worth of things that we can do for customers, or you're not finding it on one of our distributors, you could go on the Omnetics website and just look for your local rep. Like I said, we've got reps across the globe. That's a great way. Otherwise, I can put my information up too for this, and then somebody can reach out to me and I can get you lined up to where you need to be as well. We can get it figured out.
Fantastic. Thank you ever so much for taking the time to see us today.